So the next thing I want to do is to talk about what it means for two vectors, say v1 and v2, to be what's called orthonormal. So two vectors v1 and v2 are orthonormal. Orthogonal, orthonormal, means orthogonal plus each of them are unit length. So orthogonal means that the angle between them is 90 degrees, or equivalently, like we talked about, their dot product is 0. And to be orthonormal, we also want them to have unit length. So the length of the vector v1 and v2 is going to be 1. Okay, so they're both unit length. So for example, if I were to talk about the vectors, let's say, let's use u and v, so I don't have to do subscripts, but say 1 and 2, and 2 and -1. U and v are orthogonal, but not orthonormal. And they're not orthonormal because the length of u and the length of v are square root of 5. So if you wanted to make them orthonormal, what you could do is you could scale them so that they still have the same angle between them, but now they're just shorter length. Okay, and so if you wanted to scale them and make them unit length, how could you do that? Well, it's very easy. What you do is you take a vector and you divide by its length so that it's going to have length 1. So for example, the length of u is the square root of 1 squared plus 2 squared. So that's the square root of 5. And therefore, if I were to look at the vector, let's call it w, if I were to look at the vector w, which is 1 over square root of 5 times u, think about how the magnitude of that vector would be computed. You could do this in one of a few ways, but I think the easiest is you take the absolute value of your dilation factor. Okay, so 1 over square root of 5. So the direction that it faces, whether it's in the forward or negative direction, it's not going to matter as far as the length goes, times the length of u. And so this is 1 over square root of 5 times square root of 5, which is 1. And indeed, we can check that 1 over square root of 5 times u is going to be 1 over square root of 5, comma, 2 over square root of 5. And if that's our vector w, then the length of w, the magnitude, is going to be the square root of the sums of the squares of the components, just like this works before. So if I take 1 over square root of 5 and square it, we get 1/5. And if I take 2 over square root of 5, I get 2 squared over square root of 5 squared. So that's 4/5. And they really do add up to 1. Okay, so the length of the vector w is 1. So normalizing a vector means changing it so that it's got unit length. You can normalize any vector that you want, except for the 0 vector. It's the only vector with 0 length, so you can't normalize that. But any other vector, if it's got a length, you can change it so that its length is 1 just by dilating it. And so this is what's called normalizing. And so if you start with an orthogonal set of vectors, let's say w and z are the adjusted orthonormal vectors. So if I were to take, let's just, the naming thing is getting a little bit silly, but let's take u and v and then normalize them. And so if I take u, I'm going to change it to be 1 over square root of 5 times 2 over square root of 5. And then v is going to be the vector, say, 2 over square root of 5, comma, -1 over square root of 5. You can check that all I've done is dilate these vectors. And so they're still going to be orthogonal, and they're both unit length. So u and v are, in fact, orthonormal. Okay, and so that's that. So that's what orthonormal vectors are. One of the things that we're going to want to work on is starting with a basis for our vector space Rn. If I take a set of vectors, say I'm working in R5. Okay, so say I'm working in R5, and what I have is I want to think about a vector space spanned by u, v, and w. right? So I have 3 vectors in R5. Let's say, just assume for sake of argument that they're all linearly independent. And so the span of those 3 vectors will be a 3-dimensional subspace of R5. Now, these vectors as a whole may or may not be, but probably won't be orthogonal, and almost definitely won't be orthonormal. But it turns out that there's a process that you can use to turn any arbitrary basis of a subspace into an orthonormal basis. And orthonormal bases are extremely helpful and very useful for lots of things that we want to do. In fact, if we think about the standard basis, so just think about R3, what's the standard basis for R3? Well, then we have E1, which is the vector 1, 0, 0, E2, which is the vector 0, 1, 0, and E3 is the vector 0, 0, 1. And we know that this is the standard basis in that it has a lot of nice properties. For example, if I want to take any arbitrary vector, so 4, -7, and 2, and I want to write that vector as a linear combination of the vectors E1, E2, and E3, it's super easy to do that. This is 4E1 plus -7E2 plus 2E3, right? Super easy, not a lot of algebra. If I had a different basis here, so if I had a different basis, then this, could be a little bit trickier to do, but it turns out that there's a nice trick. If you have an orthonormal basis, there's a nice trick for figuring out how to write an arbitrary vector as a sum of the basis elements. This is a linear combination of the basis vectors. Okay, so the trick here is that if, let's say I almost want to wait to write this in general, but I've kind of teed this up a little bit here. So let me just give you an example, and then I'll still kind of wait to define this in general. But let's say I have 3 basis vectors. Let's say, just make this a little bit more complicated. Let's say E is going to be 1 over the square root of 2, -1 over the square root of 2, 0. Let's say E2 is going to be 1 over the square root of 2, 1 over the square root of 2, 0. So those are both they're both orthogonal and unit line, so they're orthonormal so far. And then let's let E3 be the vector 0, 0, -1. Okay, so here we have 3 vectors. None of these are the standard basis vectors, but these 3 span R3. And if I want to take any vector at all, say I want to take, just again, 4, -7, 2, and I'm going to write it as a linear combination of these vectors, it turns out what you can do. So if I take 4, -7, and 2, it turns out what you can do, and this trick only works if you have an orthonormal basis. You have to modify it a little bit if you have an orthogonal basis. This doesn't work at all if you don't have an orthogonal basis. But it turns out it works really nicely if you have an orthonormal basis. And what you do is you take this vector, let's call it V, and you take the dot product of V times E1, and then you multiply that by E1. So this V dot E1 is going to give you some scalar, and then you multiply that by E1, and then you do this for the others. You take V dotted with E2 times E2 plus V dotted with E3 times E3. And that's, if you think about it, essentially what we did before when we found those numbers 4, -7, and 2. What we did, even if you didn't think about it exactly like this, is we took the vector 4, -7, 2, and we took the dot product of this vector with each of these 3 basis vectors. So the dot product of 4, -7, 2 with the standard basis vector 1, 0, 0, the dot product is 4. And the dot product with that vector V and E2 is -7, and the dot product with the last one is 2. So we're going to do this now with our same vector V, but with a different orthonormal basis for R3. And if I take the dot product of V times E1, I'm going to get 4 divided by square root of 2 minus 7 times -1 over square root of 2. So that's going to be 4 over square root of 2 plus 7, so 11 over square root of 2. And that'll be times E1. So we'll figure out what that is all in a second. We're going to add to that V dotted with E2. So that's going to be 4 minus 7 over square root of 2, so negative 3 over square root of 2. It's too much there. So negative 3 over square root of 2 times e2. So that's 1 over square root of 2, 1 over square root of 2, 0, plus v dotted with e3. So that's going to be 0 plus 0 plus negative 2 times 0, 0, 1. Okay, and then let's just check that all this adds up. And this should be, sorry, 0, 0, negative 1. So let's just check that this all adds up the way that we want it to. And so if I look at, let's say, component by component, so this will be really easy just to check. If I take 11 over square root of 2 times 1 over square root of 2, that's going to be 11 halves minus 3 halves. So that's going to be 8 halves, which is 4. So far, so good. And then negative 11 halves minus 3 halves. So again, the half is from the square root of 2 times square root of 2. You get negative 11 halves minus 3 halves will be negative 14 halves, so negative 7. And then we get 0, 0, and positive 2. And so it turns out that orthonormal bases are super helpful for kind of decomposing an arbitrary vector into a linear combination of the basis vectors. Okay, so that's one of the things that they're going to be very useful for. And so one of the things that we're going to want to do in our study in chapter 5 here is if I have, say, some basis in R3, so maybe I have a vector, something that looks like, let's draw the basis vectors here, but let's say I have a vector that points in this direction, and then one that points kind of up and away in that direction. As long as none of them are on, so if you take any two vectors, those uniquely determine a plane, and as long as all three vectors aren't on the same plane, then they'll form a basis here, as long as we're talking about different vectors, because one is not a linear combination of the other. Okay, and so as long as they're all linearly independent, everything's fine. And so here, those three basis vectors are in kind of some arbitrary direction, but they're not going to be orthogonal. And so what you can do is there's a method for taking an arbitrary basis and turning it into an orthogonal basis. And then once you have an orthogonal basis, you can normalize each of the vectors, divide by their lengths, to make it an orthonormal basis. And orthonormal bases are very nice, okay, very convenient for a lot of calculations that we're going to do. So that's going to be one of the big things that we're going to work on. So let's get to work on that. And we've already pretty much laid all the groundwork for what we need. But the idea here is we want to start with the basis B. So we're going to start with the basis B, which is going to contain vectors, say, v1 to vn. We can do this kind of, if we do this arbitrarily for any n-dimensional vector space Rn, then, you know, the more arbitrary we can do there, the more general we can do this, the better, I mean. So we're going to start with this basis, and then we're going to construct an orthogonal basis, which I'll call B prime. And that's going to have the vectors u1 to un. Okay, so this is when I say an orthogonal basis, I need to be a little bit clear here. I talked about what it means for two vectors to be orthogonal to each other. But if I have three vectors, to say that they're all orthogonal is to say that they're mutually orthogonal. So what I mean by that is that if you take any two of them, they're orthogonal. So pick any two vectors out of this orthogonal basis u1 to un, for example. If I pick any two of them, they're going to be orthogonal. Okay, any two different vectors. Obviously, if I pick the same vector with itself and I take its dot product, I get its length squared. But otherwise, if I pick any two vectors, the angle between them will be 90 degrees. So what we're going to do here is we're going to take our basis B, we're going to orthogonalize it, right? We're going to make it an orthogonal basis. And then once you do that, then it's one small step to make it an orthonormal basis. So you normalize to make it an orthonormal basis, which we can call B double prime. And usually for orthogonal, we use E to talk about the fact that these all have unit length. Okay, I don't know why E gets used, but that's typically what gets used. So I'm going to continue with that tradition. So here's how this process works. And by the way, this process has a name. When you do something in math that's really hard, you get it named after you. So this is named after two mathematicians, Gram and Schmidt. Okay, and naming things in math is a little bit strange. Gram and Schmidt were probably the first ones to write it down, or the first ones to do special cases. But this was known before Gram and Schmidt. So yeah, naming things in math is a little bit strange. Anyways, so this is called the Gram-Schmidt orthogonalization process, or sometimes just called the Gram-Schmidt process. And the idea is if you start with the vectors v1 to vn, so here we need v1 and v2 and all the way up to vn to be linearly independent. So they have to be basis vectors. So they have to span whatever space and be linearly independent. What you can do is to orthogonalize, you do the following process. So u1 is just v1. There's no change that we need to do there. Okay. u2 is going to be v2 minus the projection of v2 on u1. Okay, so minus the projection of v2 onto u1. And if you think about v2 minus the projection, that's going to turn out to be orthogonal to u1. Okay, u1 and v1 are the same. I want to basically think of the u's as we go along here. And then we just do this over and over. And then u3 is going to be v3 minus the projection of v3 on u1, and then minus the projection of v3 on u2. And notice that u1 and v1 are the same, so there's no confusion there. But notice that I'm projecting v3 onto u2, not onto v2, but onto u2. Okay, and so that's important there. And then this continues the way that you think it does. Okay, so u4 would be v4 minus the projection of v4 onto u1, minus the projection of v4 onto u2, minus the projection of v4 onto u3, and so on. And so this process gives you those vectors u1 up to un that are going to be orthogonal to each other. So they're mutually orthogonal. And I think it's worth just kind of checking as we go along that these are orthogonal. So I'll leave this to you because it's just a nice computational exercise, but compute. So I gave you a formula for the projection. So figure out what that is when you plug in v2, and then just check that u1 dotted with u2 really is 0. Okay, and so you can go through and you can do each of these and just check that this really does work. Okay, there's a nice little bit of geometry here. So once you do that, then you can normalize each of the vectors. So of course, each of these vectors e sub I is just going to be u sub I divided by its length. Okay, so this is for all I. So not much of a surprise there. So the last step is the easy one where you just have to normalize everything. So what I want to do is I want to start with an arbitrary set of vectors. So let's actually do this process. I want to show you how this works in general, but let's actually do this process with the vectors. So with the basis vectors, let's see, I want to take v1 to be 1, 1, 1. I want v2 to be 0, 1, 1. And I want v3 to be 0, 0, 1. Okay, and what this will do is this will give me an orthonormal basis. Now, not all orthonormal bases work equally well in every situation. For example, you might need to have an orthonormal basis that's not on the axes angles, but maybe it's at a slight angle, right? It's not on the axes, I mean, but maybe it's at a slight angle. And so this Gram-Schmidt process is not just for coming up with an orthonormal basis. Of course, the standard basis would be fine every time if that worked. But sometimes we need it so that the first basis vector is in the same direction as, in this case, v1. Okay, so when we say u1 is v1, that's actually one of the strengths of Gram-Schmidt here is that the first basis vector, we're not changing the direction of the first basis vector. Okay, so this is a little bit more general than that. So let's go ahead and let's do this. So this is our, I'm gonna just call this V1, V2, and V3. And so U1 is just gonna be V1, so 1, 1, 1. And U2 is gonna be, let me make sure that's clearly a U. U2 is gonna be V2 minus the projection of V2 onto U1. And so let's remember how that works exactly, but the projection of V2 onto U1, we're going to take, so this is going to be U1 dotted with V2 divided by U1 dotted with U1 times U1. Okay, so that's how that's going to work. I think when I defined the projection, I had the V as the in the base, and then the U was in the inside. Here they're switched. It's just a formula. It doesn't matter if I switch the role of X and Y, but that's how that's going to work. And so U1 dotted with, so U1 dotted with V2 is going to be, let's see, 1 times 0 plus 1 times 1 plus 1 times 1. So that'll be 2. This is going to be 0, 1, 1 minus 2. The length of U1 is going to be, so the length of U1 squared is going to be 3. It's 1 plus 1 plus 1 times U1, which was 1, 1, 1. And so that's going to be 0 minus 2/3, 1 minus 2/3, and 1 minus 2/3. So that's our U2. And notice that U1 and U2 are orthogonal, right? If I take 1 times negative 2/3 is negative 2/3, plus 1 times 1/3, plus 1 times 1/3. So we get negative 2/3 plus a third plus a third. We really do get 0. And now let's do this again, and let's work with U3. So U3 is going to be V3 minus the projection of V3 on U1 minus the projection of V3 on U2. And so V3 is this vector 0, 0, 1. And then if I subtract the projection of V3 onto U1, this is going to be U1 dotted with V3 divided by U1 dotted with itself times U1, and then minus U2 dotted with V3 over U2 dot U2 times U2. Okay, and so this is going to be 0, 0, 1 minus, let's see, V3 was 0, 0, 1. Dotted with U1 is going to be just 1. U1 dotted with itself is still 3, and U1 is still 1, 1, 1. Okay, now subtract U2 dotted with V3. Remember, U2 is this new vector that we found, negative 2/3, 1/3, 1/3. So if I dot that with V3, that's going to be 0 plus 0 plus 1/3. So it's 1/3. And then if I take the length of U2 squared, so it's going to be, let's see, what's that going to be? That's going to be negative 2/3 squared. So it'll be 4/9 plus 1/9 plus 1/9. So it's 6/9 or 2/3. Okay, so that's U2 dot U2 times U2, which was negative 2/3, 1/3, 1/3. Okay, so that's going to end up being, we'll do this all together, 0, 1, 1 minus 1/3, 1/3, 1/3. And then 1/3 over 2/3 is 1/2. So this will be minus, let's see, negative 1/3, positive 1/6, positive 1/6. And then finally, if we put all this together, we end up with, so 0 minus 1/3 plus 1/3 will be 0. 0 minus 1/3 minus 1/6 will be, let's see, negative 1/3 minus 1/6 should be negative 1/2. Okay. And then 1 minus 1/3 is 2/3. Minus 1/6 should be positive 1/2. Okay, so we get 0, negative 1/2, 1/2. So we started with the vectors v. We ended up with u1 being the same, being the same 1, 1, 1. u2 was this vector negative 2/3, 1/3, 1/3. u3 was the vector 0, negative 1/2, 1/2. And I think it's just nice to stop for just 1 second and just really appreciate the fact that all of these vectors have, they're all mutually orthogonal. Okay, so this was the hard part, was finding these mutually orthogonal vectors. So we've already talked about u1 and u2 being orthogonal, but let's just check. If I take u1 dot u3, that's going to be 0, minus 1/2, plus 1/2. So that'll be 0. So u1 and u3 are orthogonal. And then u2 and u3 are going to be orthogonal because we get 0, negative 1/6, plus 1/6. So add those up, we obviously get 0 as well. So u1, u2, and u3 are really the orthogonal vectors that we get from this Gram-Schmidt process. And what we can do now is the final step and just normalize each of these vectors. So just divide by their magnitude. And so the magnitude of u1 is going to be square root of 3. The magnitude of u2 is going to be, what did we say it was? 4/9 plus 1/9, so 2/3, so square root of 2/3. And the magnitude of u3 is going to be 1/4 plus 1/4, so it's 1/2. And we take a square root, so 1 over square root of 2. And so what turns out we get here is that E1, this is the easiest one to do, is going to be 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. E2, we're going to take these values and divide by square root of 2 over square root of 3. So we're going to multiply by square root of 3 over square root of 2. So we're going to end up with negative 2 over square root of 6. So what I'm thinking of when I do these here, just to show you how this will work, I'm multiplying by square root of 3 over square root of 2. Now, square root of 3 over 3 is just 1 over square root of 3. And then square root of 3 times square root of 2 is square root of 6. So we got negative 2 over square root of 6, 1 over square root of 6, 1 over square root of 6. Okay, so that's the vector E3, E2, I mean. And then E3, we're going to take each of these vectors and we're going to multiply by square root of 2. So we get 0, negative 1 over square root of 2, 1 over square root of 2. And again, when we're normalizing, when we're dilating vectors, we're not changing the direction, so the orthogonality relations are preserved. Okay, and so that's Gram-Schmidt for these vectors in R3. Okay, the last thing I want to say here is I want to talk about what's called the orthogonal complement. So let's actually do that in the next video, because I feel like this is getting just a little bit long. So in the next video, we'll talk about the orthogonal complement of a subspace.